Hi AP Stats students, we are starting our next section in this unit on collecting data. In our first section we talked all about sampling and surveys. In this section we're going to be focusing on experiments. Now you probably know a lot about experiments based on general science classes that you've taken, so some of this might sound familiar, but a lot of this vocabulary is going to be unique to AP Statistics and will maybe help you understand experiments in a better way. Here are our learning targets by the end of this section. You can read those here and also on your learning targets page. There are a good number of them. There will be a few videos in order for us to get through all the things on experiments. In this first one, we're going to be focusing on the difference between observational studies and experiments, and then also some of the basic language of experiments. So let's dive right in. What's the difference between an observational study and an experiment? Great question. I'd love to tell you. An observational study observes individuals and it measures variables of interest, but it does not attempt to influence the responses. The goal here is to describe some group or situation, or to compare groups, or to examine relationships between the variables. Now, sample surveys, which we discussed in the previous section, is one type of observational study. There's going to be two different types of studies you can do. You could do a retrospective one, where you examine existing data for a sample of individuals, or you could do a prospective one, is where you track individuals into the future. So kind of keep those two types in your mind. Now, we did in our previous unit on scatter plots and two sets of quantitative data talk about response variables and explanatory variables. These are still going to be present when we're talking about collecting our data here. So if you recall, a response variable is going to measure an outcome of the study. We usually put that like on our y-axis when we had quantitative data. And then the explanatory variable may help explain or predict changes in the response variable. Now, when you have two sets of quantitative data, you can display it in a scatter plot, but we're not always gathering quantitative data. Now, oftentimes, you could do everything right, but it might be hard to figure out if one thing kind of caused the other. So there's this idea of confounding. When two variables are associated in such a way that their effects on a response variable cannot be distinguished from one another. So let's look at an example here. In a recent study of about 13,900 college freshmen, a researcher found that the more time students spent drinking alcohol, the lower their grade point average. Explain how confounding makes it unreasonable to conclude that spending more time drinking causes a decrease in GPA for college freshmen. Well, it's possible that the students who spend more time drinking are also less motivated toward their academic success. Now, is this true for everybody? No, but it's possible. Also, if students with lower motivation have lower GPAs, it could be that the student's motivational level caused the GPAs to go down, not the time spent drinking alcohol. So, in this case, that lower motivation is going to be that confounding variable. It might not be the amount of alcohol that they drink that causes the lower GPA, but it might be this hidden confounding variable that might be kind of blurring our results. Especially if, this just came from, I'm assuming, a survey. I hope they didn't do an experiment in which they, assigned certain people to drink and others not, and then measure their GPA. I don't know how ethical that would be. So the fact that there was no experiment that happened is another way to be like, I don't think one caused the other. But you need to be able to identify what might be the hidden underlying thing that's kind of blurring our results. Did the explanatory really lead to this response, or was there some confounding variable? So make sure we have this idea of confounding variables straight in our minds. Let's talk about the big thing, which is going to be our experiments. Now, to be an experiment, that means you have to deliberately impose some treatment on individuals in order to measure their responses. Okay? So it can answer questions like, does aspirin reduce the chance of a heart attack? Or can yoga help you live longer? The goal here is to see whether a treatment causes a change in the response. This is probably one of the biggest things that I could teach you all year. In order to gauge cause and effect, experiments are the only source of convincing evidence. Okay? You can, see if there's a relationship if you gather data through a survey, but in order to say one thing caused the other. Experiments are the only way to do that. You still have a response variable, which we know measures the outcome of the study, and we still have the explanatory variable, which again may help explain or influence the changes in a response variable. Okay, let's kind of compare the difference between the two. We're looking at SATs and the scores and the hours that were studied. So we want to describe both a survey and an experiment that can be used to determine the relationship between SAT scores and hours studied. Pause this video, jot down a couple ideas. What could you do for a survey and what could you do for an experiment? And then once you have your thoughts written down, unpause it and see what I say. So an example of a survey, you could ask students about how many hours they studied for the SAT and then what were their results. So you didn't make them do anything. You're simply gathering data from something they already did. In an experiment, you have to impose or apply a treatment. So in this case, you would need to randomly select a group of similar or the same kind of IQ students, just, even the playing field. And then you would need to assign each student a different number of hours to study for the SAT. You would want to assign this randomly. Now, the student is only allowed to study for the mandated amount of hours, and then after they've taken the SATs, you can compare their resulting scores. Let's look at a couple more examples comparing observational studies and experiments. Does eating dinner with your family improve students' academics performance? According to an ABC News article, teenagers who eat with their families at least 5 times a week are more likely to get better grades in school. This finding was based on a sample survey conducted by researchers at Columbia University. We want to know, was this an observational study or an experiment? And then what are the explanatory and response variables? The fact that it was based on a survey tells me that it's going to be an observational study because no treatment is being imposed. They didn't say, hey, you need to eat dinner with your family this many times a week, whereas another person did another time and then measured their grades as a result. They just collected data from a survey. The explanatory variable here is going to be the number of times that they were, eating with their family per week. And then the response is going to be, it didn't really say, but I'm assuming grades, maybe GPA, something along those lines. Try this next one on your own. Pause the video and then jot down your responses. Once you have your answers written, you can unpause. So was this an observational study or an experiment? Well, this one is going to be an experiment because the researchers deliberately gave the subjects either caffeine or a placebo, which we'll talk about in a little bit. The explanatory variable here is whether or not caffeine was ingested, and the response variable was the time to complete the 10-kilometer bike ride. Notice how I didn't say the explanatory variable was just caffeine, right? It's either whether it was given or not. So you make sure you're being clear and expressing enough in your descriptions of your variables. Now, we just mentioned placebo. Let's talk more about that. The placebo is going to be a treatment that has no active ingredient, but is otherwise like other treatments. So, for example, if the treatment is taken in aspirin daily, but the control group doesn't take a pill, then that group is not being treated the same. So the control group is going to need to take a placebo so that everyone is taking a pill. Here's another example. In a baldness study, 42% of the placebo group kept or increased their hair, while 86% of the treatment group did. So the treatment was better than just thinking that you were being treated. Now, generally with people, you're going to need to do placebos. If you were, doing an experiment on plants, a placebo would not be necessary because the plant's not going to be like, oh no, I'm not getting the new fertilizer, so I'm not going to grow as much. So placebos are more used for human subjects. An experiment is a statistical study in which we actually do something to the people, animals, or objects to observe the response. So what do I mean by treatment? A treatment is when a specific condition is applied to the individuals in an experiment. If our experiment has several explanatory variables, then the treatment is going to be a combination of specific values of these variables, and we'll do some examples. Now, an experimental unit is going to be the object to which the treatment is randomly assigned. And the key here, it does need to be randomly assigned. We'll talk more about that in a future video. When the experimental units are human beings, instead of being called experimental units, we often call them our subjects. A little more humanizing. Let's go through an example. Several AP Stats students wondered whether caffeine could improve test scores. They randomly assigned 30 student volunteers to either drink regular coffee or decaf coffee the morning of the student's next test. At the end of the experiment, they recorded test scores for each student volunteer. Let's identify the treatments and the experimental units in this experiment. So the treatment, what did they get? Well, let's do the units first, sorry. Our units here are the 30 student volunteers. Right? They assigned 30 student volunteers. So 30 volunteers are our units. And then my treatments are either getting regular coffee or decaffeinated coffee. So there are 2 treatments here. Let's do another example. List the factors and the number of levels for each factor. Well, what are those things? So glad you asked. In an experiment, a factor is a variable that is manipulated and may cause a change in the response variable. The different values of a factor are going to be called the levels. So let's look at this in the context of an example. We're looking at adding fertilizer. Does that help the productivity of tomato plants? And what about water? So here's what the gardener is going to do. He plans to plant 24 similar tomato plants. He's going to add fertilizer to the soil in half of the pots, and he's going to water 8 of the plants with half a gallon, 8 with 1 gallon, and the remaining 8 with 1.5 gallons. And at the end of 3 months, he will record the total weight of tomatoes produced by each plant. So what are my factors here? My factors are whether or not fertilizer is applied and the amount of water given. Right? These are the things that I'm doing, but they can change. So yes, no fertilizer, and then how much water, half gallon, 1 gallon, or 1.5 gallons. And then the levels just tell me, how many of each factor are there. So whether or not fertilizer is applied, those are 2 levels. Yes, it's given. No, it's not. Amount of water given, there's 3 different options: half gallon, 1 gallon, or 1.5 gallons. If the researchers used every possible combination of levels to form the treatments, how many treatments were included? And then let's list them. The way that you're going to calculate how many treatments there are is you're just going to multiply the number of levels. So 2 levels for fertilizer, 3 levels for water, leaves us with 6 different treatments. So the treatments are either a plant is getting fertilizer with half a gallon, fertilizer with 1 gallon, fertilizer with 1.5 gallons, or no fertilizer with half gallon of water, no fertilizer with 1 gallon of water, and no fertilizer with 1.5 gallons of water. All right, let's really hit this home. Factor versus treatment. So for example, let's say you have 3 different groups of runners and they're subjected to different training methods. The units are going to be your runners. The factor is going to be the training methods just in general. And then the treatments are going to be the specific type of workout. So maybe speed, strength training, and distance workouts. So think of factor as the general group and treatment as the specific, implementation. And like I said, in order to determine the number of treatments, you simply multiply the number of levels for each factor. Let's wrap it up with one more example, and then we'll be finished with this video. A cookie manufacturer is trying to determine how long cookies stay fresh on store shelves and the extent to which the type of packaging and the store's temperature influences how long the cookies stay fresh. He designs a completely randomized experiment involving low and high temperatures and 2 types of packaging. List the experimental units, the factors, the treatments in this experiment. How about you try this? Give it a pause. See if you can list out these things. Okay, our experimental units are the packages of cookies. Okay, notice I didn't just say cookies or packages, it's the packages of cookies that I'm experimenting on. The factors here are going to be the temperature and the packaging, right? That's what's going to change. And we have 2 levels for each of those. And then our treatments, there's going to be 4 treatments: low temperature with plastic, high temperature with plastic, low temperature with waxed cardboard, and high temperature with waxed cardboard. All right, that concludes our first little installment about learning about experiments. I highly suggest you look at some of the example problems in the book and also some of the practice problems. In our next video, we will talk some more about how to design a good experiment.